The presenter will be Rafał Mantiuk. He's a professor of graphics and display and Department of Computer Science and Technology at Cambridge University. He received PhD from Max Planck Institute for Computer Science in Germany. His recent interest focused on computational displays, rendering, and imaging algorithm that adapt to human visual performance and deliver the best video quality given limited resources, such as computation time and bandwidth. Let's welcome.
Thank you for this introduction. So let me tell you a bit about contrast-sensitive functions, and in particular on one particular visual difference predictor, and how they could be used for optimizing media. Let me see. Okay. I can just press the key in the meantime.
Doesn't move forward?
No,
That's the problem.
Oh, no, it does.
No, let me try to go back. Now it's working.
Okay.
Just do one click.
Okay. Okay, perfect. So because some of you may not know me, let me give a brief introduction. So our research group is graphics and displays, and I'm interested in a range of topics, including perceptual graphics, computational displays, high dynamic range, applied visual perception, and so on. To give you a bit of an idea of work we do, for example, a couple years ago, we finished a large ERC-funded project on reproducing reality, where we built this enormous high dynamic range stereoscopic 3D multiplane display. And over here you can see a video of that display. It is really gigantic setup, half of the room. You can see over here a projector shining a white light on back of an LCD. And this provided a backlight for one of the 4 HDR displays. And when the observer looks at the image from the viewpiece, he can see combination of LCD modulation with the backlight, which is a nice stereoscopic 3D image. And the idea for this project was that we could capture a small scene with very high quality, with ordinary, off-the-shelf mirrorless camera, and reproduce this 3D scene with such fidelity that people couldn't tell whether what they see is real and virtual. And in this picture, you can see two simple objects side by side. One of them is real, the other is virtual. And even in a photograph, probably you cannot tell which one is which. And obviously, these were like 3D objects, floating in the air. So this is one of our research platforms that we use to study things that could be coming in the future, to study future display technology. But in general, we are interested in modeling visual system with a purpose. So modeling very basic kind of psychophysical matters regarding visual system. And I will talk more about the second topic about modeling visual perception. And just to tell you that I'm not only computer graphics, I also interested in video coding and streaming. This is a very ancient project, SIGGRAPH 2004. This was actually my first PhD project. And in the video, you can see the recording from, I believe, one of the first high dynamic range video cameras in black and white. And because we couldn't convey high dynamic range on ordinary video, we had this virtual ND filter that we can put on top of the very bright light sources just to convey how much dynamic range we could encode. And the goal of the project was to show that we could encode the entire range of visible luminance, all colors that people could see with not more than 12-bit for luma and 2 times 8-bit for chroma. And we came out with this transfer function that is suspiciously similar to Dolby PQ, perceptual quantizer, that was proposed by Dolby 11 years later. And even the plots that you can see in our paper are very similar to those you can find in Dolby paper. Anyway, When I talk about metrics we work on, I don't use the word perceptual because people say that, SSIM is perceptual, APLPS is perceptual, so, this is overloaded term. So I say that we are working on psychophysical metrics and models. Psychophysics, this is very old science, dating back into early, late 19th century. I don't know if you can recognize those two gentlemen in the corner. This is Ernst Weber and Gustav Fechner, the father of psychophysics. And psychophysics is essentially a combination of psychology, study of the brain, and physics, which obviously deals with very accurate measurements grounded in the physical world. And this is what's different because psychophysics cannot operate on abstract quantities like a pixel value from 0 to 55. It needs to operate on physical quantities of light emitted from a display. And in terms of you may think that psychophysics is a perfect tool, perfect platform for quality assessment. And I think in 90s there was this notion that psychophysics is the way to go. There are a lot of visual metrics that were based on psychophysics. And I believe everything dipped around 2000 where people had the notion that psychophysics doesn't work. It's just like visual quality is too complex, too high level. We need SSIM, those simple metrics that seem to work equally well. But I think we are slowly showing that psychophysics actually does work for visual quality. And I hope that I can convince you that psychophysics is the only way to go if we really want to generalize our quality metrics for all kinds of future display technologies. This is something that I don't need to spend too much time on because this problem where we need to find a trade-off between quality and feasibility because quality doesn't come for free. It costs computation, bandwidth, materials. So quality can go from horrible to perfect, feasibility from impossible to easily doable. And while feasibility is easy to measure, to quantify, quality is a bit more difficult to quantify. And for that, we use quality metrics. And usually our task is to find this curve and a point on a curve that allows us to build a product that is feasible and delivers decent image quality. Over here, I listed just a few examples, probably the most popular quality metrics. If you check any paper that involves quality metric, it will probably use one of those. So what's wrong with those metrics? So none of the metrics listed in this slide actually accounts for a physical specification of a display for the light it emits. And if you think about it, today people can consume content on a TV screen, on a mobile phone, or maybe on VR headset. And the pixels in each of those devices are very, very different. It's not only the size of the pixel, also contrast, luminance, color space. They're all different, and most of the metrics just ignore the fact that those images are going to be perceived very differently. Simple quality metrics like PSNR doesn't account for special pixel configurations, which is super important for quality. Not many metrics account for color. And also very few metrics account for temporal distortions. And this is an example of an artifact that you won't find in video streaming. This is an AR, optical see-through AR artifact, waveguide non-uniformity, where you have those low-frequency chromatic distortions that pop up, they are combined with a content. And if you try to use off-the-shelf quality metric like SSIM, it will just fail miserably on predicting the visual impact of this kind of distortion. So with color video VLP, we wanted to obviously tick all those boxes and deliver visual metric that addresses those shortcomings. So what is color VLP? It's a full reference quality metric that takes as input test and reference images or videos. Could be high dynamic range, could be low dynamic range. We also take as input display specification. And then we can produce three outputs, like single value quality scores, but also the spatial distortion maps telling you where those distortions are most visible, and also a histogram, which is essentially a spectrogram of distortions over time. So you can analyze, in which frequency bands those distortions are the most visible. I believe this is the first video quality metric that models both color and spatial temporal vision. It's built on psychophysical models. It's differentiable. It's written fully in PyTorch. And we calibrated in particular for video streaming, but also for display distortions, because this was the work done in collaboration with Meta Reality Labs, and they were obviously interested in display distortions. So ColorVDP is not a deep learning metric, which is quite unusual trend those days. And because of that, I can actually explain you exactly how it works, and you will see that it's actually a very simple pipeline. So what we have there, we have a display model that is specified as a simple JSON file, which will translate our input encoding, whatever it is. It could be, PQ, it could be, like regular sRGB color space, into light that is emitted from the display, because we are grounded in psychophysics, so we need to have a physical quantities of light. Then we operate in the opponent color space. In our case is DKL, very popular in vision science, and it's also a basis of our contrast sensitivity function, about which I will talk a bit later. Then we have temporal filters, and those temporal filters, they mimic mechanisms of the visual system: achromatic, sustained, achromatic, transient. One responsible for more static vision, the other is responsible for seeing differences. And what's different between ColorVDP and other metrics is that we just don't consider like two neighboring frames, but we consider a time window of 250 milliseconds. And the number of frames per second, whether this is 24 or 60 or 120 frames frames per second video, will obviously have impact on the predictions of the metric. We have multiband decomposition, very popular component of many metrics that account for spatial vision. And then the core of our metric is the model of contrast sensitivity, contrast masking, supra-threshold contrast perception, and we also model cross-channel masking. I don't have too much time to get into the technical details of contrast masking, but let me tell you about Castle's SF, because I think this is another important contribution. This is yet another model that we proposed together with ColorVDP. It's quite comprehensive model of contrast sensitivity of the visual system, telling what's the smallest contrast that human eye can see. Is the function of chromatic modulation, area, spatial frequency, temporal frequency, luminance, and eccentricity, all of those forming the word Castle. That's why we call it Castle's SF. And to give you a bit an idea what this model does, let me bring analogy to McAdam ellipses. You probably are familiar with the concept of McAdam ellipses, so the smallest difference in color that is visible to the human eye. And McAdams measured those ellipses for maybe 24 different colors. What we can do, we can generalize his measurements to any luminance level, to any color, to any spatial frequency, to any viewing distance. So we can generalize those smallest detectable differences to any configuration of a stimuli. Our metric doesn't return quality in arbitrary units. We scale quality in units what we call just objectionable differences. They are similar to GNDs, and they are designed in such a way that one GND difference gives us 50% preference across the population. So it's nice because it's interpretable unit that gives you the quality improvement of one algorithm over the other one. A bit kind of more general view on the on modeling visual qualities. So if you think about majority of those simple quality metrics like PSNR, SSM, and so on, they take as input digital image in pixel values from 0 to 55 and try to find a correlation with a quality. Very few metrics actually account for the display model, for the physical specification of the display, and even fewer metrics actually account for the psychophysics of the visual system. And if you think about it, those factors are there. We always have display, we always have visual system. Why should we skip them? Why should we actually ignore those? And my argument for actually modeling both display and psychophysics is that when you try to train a model on the data set, your deep learning framework is very likely to pick up correlations, but not necessarily causation. If you have a model grounded in psychophysics and physics, you have much better chance of capturing causation. About the performance, ColorVideoP, it performs quite well. We trained it only on 2 data sets and tested on those listed, but many more data sets later. It outperforms VMAF on our data sets, especially on the display distortion data set. And compared to simple metrics like PSNR or SSIM, we are obviously much, much better. But I don't like those single quality numbers, like a single number, explaining the performance of the metric, because they hide many things that actually relevant for us. So what we like to do, we like to test quality metrics on those simple patterns, for example, band-limited noise of different contrast and spatial frequency, and input it as a test image, and then the reference would be a uniform patch. And then we collect the responses of each quality metric. For example, you can see that PSNR will respond to contrast, but is completely insensitive to spatial frequencies, so it doesn't model contrast sensitivity. SSIM is very sensitive to high spatial frequencies, but if you look at this chart, you can see that actually we don't see anything in high spatial frequencies. We are more sensitive to the medium frequencies, so it shows that SSIM is completely wrong when modeling spatial contrast sensitivity. LPIPS, it did learn something. It's very noisy. It's not really, monotonic, but it has some shape. And ColorVideoP obviously explicitly models contrast sensitivity, so you get the sensitivity that is well aligned with what we see the best. Masking is super important. So another short example. So the dashed line is the psychophysical measurement from one of the papers, and you want the contour lines to actually follow this dashed line. PSNR doesn't model masking. SSIM, interestingly, it does model some components of masking, so maybe that's why it performs better in some of the tests. LPIPS, this was really surprising to me. LPS did train it did actually learn how to perform masking. It's not very regular, it's quite noisy, but it has the right shape. And ColorVideoP obviously explicitly models masking, so it has the right response. And the last example, because obviously our focus was on color, so I'm showing you the square wave, where the amplitude of a square wave was selected in such a way that the perceived magnitude of a square wave is the same in each row. And you would expect that for those patterns, metric has the same response. And when we test, for example, flip, which is a popular metric in computer graphics, you can see that flip is super sensitive to yellow-violet color direction, but not sensitive enough to chromatic direction. And ColorVideoP gives us those nice flat responses as we would expect. I mentioned that ColorVideoP is differentiable. 5 minutes? Okay. I will be quick. Can we use that as a loss function? And this is an example where we do adaptive chroma sampling. Chroma subsampling is, it's very common. Everybody knows how it works. But on some content, it will introduce visible artifacts. So why don't we actually adaptively blur our CB and CR planes in such a way that we get rid of those high spatial frequencies, but without affecting the parts of an image that would result in visible changes. So what we are doing, we are finding an image for which the gradients of CB and CR are as small as possible. So we have L1 prior to enforce sparsity. And at the same time, we want the optimized image to be similar to the original in terms of ColorVideoP. And as you can see, you can smooth those images quite well, improve coding performance without affecting a color image. So you may think, that's great. This is the best loss function. We can use it in all kinds of problems. And the answer is unfortunately not always, because what we observe is that when we try to use not only ColorVideoP, but also LPIPS and all those perceptual loss functions, they make the loss landscape of the optimization problem much more complex. And you are much more likely to end up in a local minima rather than in a global minimum. Therefore, ColorVP could be used for optimization, but extra precautions need to be taken, and maybe not most straightforward optimization methods needs to be employed. And finally, very quickly, ColorVP is not perfect. It has limitations because it models only low-level human vision. It doesn't model any high-level elements of human vision. For example, saliency. If you look at the scene, nobody's going to pay attention to something happening in the background. Everybody's paying attention to the lady sitting on the bench. Another problem is sensitivity to differences in textures. If you have, a texture of a grass, pixel by pixel, they are different. For human observer, they look the same. What can we do? Obviously, if we don't know what to do, we drop machine learning. So this is what we did. We use ColorVP as our backbone because it provides all the psychophysics, all the display modeling, and so on. Then we encode the response of ColorVP as features by computing mean and standard deviation in just patches, by small patches of the same size. And then we pass it to multi-layer perceptron or transformer or whatever is your favorite machine learning regressor. And then, this was actually submitted for the ICME Grind Challenge. And we did quite well in that challenge. We trained on 4 data sets, validated on 5 other ones. I'm not going to look into all the kind of details of the results. But we did quite well. We got the second place, not the first place. We didn't have the biggest transformer network employed. But I'm skeptical. Why? Because this is this kind of the CSF test where you have patterns of different spatial frequencies, and you can see that ColorVP has these nice continuous lines. But when we try 2 versions of our machine learning model, we have those islands, those non-consistent, non-convex functions. So it's clearly we can, machine learning is great if you want to win a challenge, but not so great if you want to generalize for all kinds of content that you may want to deal with. So to summarize, ColorVP is a full reference metric for images and video, SDR and HDR, is display adaptive. It can adapt to viewing conditioning. It's fast to compute if you run it on GPU. It's differentiable. It's fully interpretable white box. And everything is publicly available on the at the MIT license. Thank you.
Can I take one question from the room? Go ahead, please. There's a mic.
So you talk about psychophysical factors, right? But also in your model, you also have display awareness, right? So how much benefits come from display part? That you're aware about display as opposed to human vision.
Yeah. We had a paper last year at QMX that showing that display, the viewing distance, the display brightness changes your quality score a lot. So this is very, very strong effect, and there's no question about it. I would answer just yes. The display does matter, and you need to have that in mind. Whether this is we model it reasonably well. Whether this is the best way to model display activities is kind of open question.
Thank you. Thank you.
Let's thank the speaker again.